Suppose that we have a positively charged particle moving through a magnetic field with the velocity of v. That moving charge will experience a magnetic force that deflects it at a right angle that is perpendicular to both its motion and to the magnetic field. Well, let's think about it. Remember, a moving charge generates a magnetic field. So what if you have a moving charge that is in the magnetic field of another moving charge? Well, that moving charge will generate its own magnetic field. And when the two magnetic fields interact, they will create a magnetic force. So the magnetic force on this moving charge is always at a right angle to the motion, rather the velocity of the charge, and at a right angle to the magnetic field. So that means that this magnetic force will deflect the particle from its path, causing the particle to turn, but since it's always at the right angle to the particle's velocity, it will never cause the particle to speed up. That magnetic force is equal to the product of the particle's charge and the cross product between its velocity and the magnetic field. Now let's explore this with the following example. At a certain point on Earth's surface, Earth's magnetic field has a magnitude of 5.0 times 10 to the minus 5 teslas and points upward and toward the north at an angle of 55 degrees above the horizontal. A cosmic ray muon with the same charge as an electron and a mass of 1.9 times 10 to the minus 28 kilograms is moving directly down toward Earth's surface with a speed of 4.5 times 10 to the 7th meters per second. What is the magnitude and direction of Earth's magnetic force on the muon? Let's begin with a sketch. We'll start off with Earth's surface. Now, because we are dealing with magnetic forces and magnetic fields, it's likely that we're going to have to develop our three-dimensional coordinate system, or at least define it. Since we're given direction in terms of north and up and down, let's do our coordinate system where the horizontal axis corresponds to the direction of north, while the vertical axis corresponds to up or down. We'll call that the y-axis. And east and west will be the axis coming straight out of the screen, where east is coming towards us and west is going away from us. So this is what the compass rose would look like. And if we were looking straight down from above the Earth's surface, this compass rose would look like this: north to the right, east down, south to the left, and west to the upper part of that screen as we are looking down from the positive y-axis. We're told that at a certain point on Earth's surface, the magnetic field points upward and northward, as indicated by our magnetic field lines. These lines are indicating a uniform magnetic field, and we will label the direction as being equal to 55 degrees above the horizontal. We are given that a cosmic ray muon is headed straight down towards Earth's surface. The speed at which this muon is moving is 4.5 times 10 to the 7th meters per second. Now, muons are charged particles. The charge of this muon is given as the charge of an electron, which we will represent the charge as being equal to Q is minus E. We're further told that the muon has a mass, and the mass of this muon is equal to 1.9 times 10 to the minus 28 kilograms. And we're told that the magnitude of the magnetic field is 5.0 times 10 to the minus 5 teslas. Using this information, we have to determine the direction of the magnetic force that the Earth exerts on the muon. So notice we have a charged particle moving across magnetic field lines. Whenever a charged particle moves across magnetic field lines, we know that it's going to experience a magnetic force given by this relationship. It is equal to the product of the charge and the cross product between the charge's velocity and the external magnetic field, in this case, the magnetic field of the Earth. Due to the cross product, we know that the magnetic force that Earth exerts on this charged particle will be at a right angle to the charged particle. Since we know the angle of the magnetic field with the horizontal and the direction in which the charged particle is moving, let's use the version of this magnetic force that involves the magnitude of the cross product between the particle's velocity and the magnetic field, which would be the charge of the particle times the magnitude of the muon's velocity, which is its speed, times the magnitude of Earth's magnetic field, times the sine of the angle between the particle's velocity and Earth's magnetic field, and the direction will be given by the right-hand rule. The version of the right-hand rule that I'm going to use is basically a 4-part sequence. It starts off with by saying, place the fingers of your right hand in the direction of the particle's velocity. So let's say this is my right hand, and we will put this in the direction of the particle's velocity, which is straight down. That's step 1 of the right-hand rule. Step 2 of the right-hand rule says, try to curl your fingers in the direction of the magnetic field. The purpose of this is just to align our palms in a direction so we can actually curl towards the magnetic field. This means that we face our palm towards the magnetic field, and then we try to curl our fingers. So when we curl our fingers, and then we stick our thumb out, the direction that our thumb points is the direction of the magnetic force due to the charged particle. So again, downward faces the direction of velocity. Our palm then faces the direction of the magnetic field. Our thumbs then face the direction of the magnetic force. So here our thumb is pointing straight along the east axis. Now that would be out of the screen, coming right at you as you're watching this video. Since our thumb is pointing parallel to the east axis, we know from the right-hand rule that the direction of the magnetic force is east. I should point out that this east direction is the direction of the magnetic force on a positive particle, because the right-hand rule for a magnetic force due to a magnetic field gives you the direction of the magnetic force that a positive particle would experience. Now this muon is negatively charged. What that means is the direction of the magnetic force on the muon is opposite to the direction given to us by the right-hand rule. So the actual direction when we write down our final answer should be in the westward direction for this muon. Now, I'm not worried about that right now because since the charge is negative, the Q is negative, when I put that negative into my final answer, it'll flip the east direction to the west direction. But this will be our reality check. Our final answer should be west because that is opposite the direction that our thumb is pointing as given to us by the right-hand rule. Now that we know the direction of the magnetic force on the charged particle, let's apply the information we have to determine the magnitude of the magnetic force. The magnetic force is given by the charge times its speed times the magnitude of the magnetic field times the sine of the angle between the magnetic field and the charge's velocity, and we know this is in the east direction. So another thing we need to do before we plug in our values is to determine the angle between the charge's velocity and the magnetic field. So let's look at that. The charge is moving straight down. The magnetic field is at an angle of 55 degrees above horizontal. This means that the reference angle between the magnetic field and the charge's velocity is 35 degrees. So we have the angle between the velocity and the magnetic field, or the reference angle rather, is equal to 35 degrees. We now have enough information to determine the magnetic force due to Earth's magnetic field on this muon. The magnetic force is equal to the muon's charge, which is the charge of an electron, given as 1.602 times 10 to the minus 19 coulombs. This is multiplied to the charge's velocity, which is moving at 4.5 times 10 to the 7th meters per second. Earth's magnetic field, the magnitude of which is 5.0 times 10 to the minus 5th Tesla, and the sine of the angle between the muon's velocity and Earth's magnetic field, which is 35 degrees. The direction of this magnetic force is east. Doing a unit check, I see that we have a coulomb meter per second Tesla, which is the unit of Newton. After plugging this into my calculator, I get that the magnetic force on the muon is minus 2.1 times 10 to the minus 16 newtons east. But wait a minute. Remember, east was the direction that we got from our right-hand rule. Now, the right-hand rule is applied to positive charges. Well, a muon is negatively charged. So when we got that the direction of our thumb was parallel to the east axis, since a muon is negatively charged, that would mean the magnetic force is actually opposite the direction that our thumb would tell us from the right-hand rule. So that would be westward. The muon experiences a magnetic force westward. Now, this result indicates that because this minus in front of 2.1 times 10 to the minus 16 newtons really flips the direction of our magnetic field, or rather, it flips the direction that we determined with the right-hand rule. Because of that, we could say that the magnetic force on the muon is equal to 2.1 times 10 to the minus 16 newtons west.